Theoretical physics is usually something that is regarded as quite obtuse and abstract, but Professor Sir John Pendry has translated the deep physics into some very significant concepts that have captured the imagination of the physics community and the broader community, as indicated through the recent press associated with the cloaking concept, which you'll hear about tonight. He began his career in the Cavendish Lab in Cambridge, followed by 6 years at the Desbury Laboratory in Cheshire, where he was head of the theory group. Since 1981, he has worked at Blackett Laboratory at the Imperial College of London. That's a very distinguished laboratory. And his team are indeed credited with creating the first practical invisibility cloak. And I should point out that John has a very distinguished career that has gone over a number of decades, where he has made significant contributions in a number of areas. His field has indeed been very distinguished. Recently he served as the Dean of the Royal College of Science and the head of the department at Imperial College, again a very prestigious position, and subsequently Principal of the Faculty of Physical Sciences. He's won numerous prizes for his work, among them the Dirac Medal, the Descartes Prize. In 1989 he was named a Fellow of the Royal Society, and in 2004 he was knighted for his services to science. And again, it's an obvious question, will there be a Nobel Prize for the science that we're going to hear tonight? Last year, Professor Pendry's distinguished career as a scientist was celebrated at Pendry Fest, so you know you've made it when they celebrate with an event with your name, a UK event which paid homage to the extraordinary depth and breadth of Professor Pendry's contribution to physics over the past 40 years. So we're delighted to have him here today to tell us about his work, and I invite Professor Sir John Pendry to the podium.
Well, thank you, Ben, for that glowing introduction. I'm wondering whether I can actually live up to it. It's a pleasure to be here in Sydney and to see Australian science in such obvious good health with the interest of so many people. I want to tell you about some ideas which our team has been developing to do with light and electromagnetism generally. We have some ideas about new materials in optics and some design tools, how to use those materials. But that would be rather dry basis for a lecture. So when we got all excited about these new ideas, we asked ourselves, how can we convey this excitement to other people? What can we actually do with these new techniques? So suddenly we came up with the idea we could hide something, we could make something invisible. And my wife said, "You mean like Harry Potter?" Who's Harry Potter? And so this connection with invisibility was born. It's interesting to ask why people find it exciting and unusual and surprising that something can be made invisible. And I think it has to do with the fact that light is our primary means of getting information from the world. Our brain makes all sorts of assumptions about what light does, and when those assumptions are broken, we're surprised and shocked. And that's why invisibility, although, as I hope to show you, it's something that's perfectly understandable and obeys the laws of science and so on and so forth, nevertheless, we surprise and I hope delight in the fact that something can be made invisible. In fact, this fascination with light is something which has been present for as long as man has written about science, to the extent that you might wonder, is there anything new to be done in optics? So before I get on to the invisibility part of my talk, I'll just quickly go through a number of the distinguished ancients who have contributed to optics. And in fact, I'm going to touch on their contributions at various stages in my lecture. So we're going to have to refract light to make something invisible. And this guy, Snell, told us how light refracts in an interface. Those of you who do high school physics, some stage will come across Snells Law, which is a law that governs refraction at an interface. Actually, if you're French, you call this Descartes' law, because they actually invented it at the same time. Having won the Descartes Prize, I feel I have to mention that to you. So, Descartes-Snell law of refraction. So we're going to bump into that as we go along. What else? Yes. Oh, this guy, yeah. He got into everything. There we see Newton in Neller's famous portrait, Newton in his prime, in his 40s. Gosh, what that conveys. Conveys intelligence. It conveys aggression, I think. He was not a nice man. So you can't have everything. However, here's one of the things he did. This is from his optics treatise, and we celebrated the 300th anniversary of its publication a few years ago. This is one of the experiments enhanced in Photoshop, which shows the experiment that Newton did. Here is a knot hole in the shutters of his room in Trinity College, Cambridge. And it's a wonder he got anything done, actually, because he could only do experiments when the sun shone. He should have moved to Australia, obviously. So he refracted light through a prism and split it up into its component colors. And then what he did was to select one of those colors and to try and split that up again. And he couldn't do that. And in his own words, and in these 3 experiments, it is father very remarkable that the color of the homogeneal light, by which he means this selected bit here, was never changed by the refraction. And translated into modern language, what that means is if the light has a certain frequency or beat in time, that beat does not change in the sort of experiments which he did. It's very difficult to change the frequency of the light. So once you've selected that frequency, any more bits and pieces of prisms and so on cannot change the frequency. So this conservation of the frequency or energy of the light is a fairly central thing in optics. And we'll talk about dispersion as well. Galileo, he was an important guy. He didn't invent the lens, but he made a lens more perfect than anybody had done before. It was so perfect that for the first time he could observe the moons of Jupiter, and he named them after his patrons. By the way, I wonder if you know where the name lens comes from. It comes from this little bean here, which is the lentil, which is a staple of food in the Middle East, and you can see that it is lenticular in shape, and hence the name lens. Who else? Fermat. Fermat is famous for many things. Fermat's last theorem took several hundred years to prove and was only proved about 10 years ago by Andrew Wiles. But one of the many things he did was to look at optics in a very unusual and original way. And he asked, well, how can you predict how the rays of light will move through a lens? So you've got an object here and an image here. And he said that the path which a ray of light chooses to take is one which minimizes the optical distance. What he meant by the optical distance was not the distance which a ruler would measure, but each distance had to take account of the fact that you're moving through a refracting medium, and you increase the length that the light sees by the factor of the refractive index. And if you do that, all these different paths through the lens that rays can take satisfy this minimum criterion here. So he had a way of thinking about the propagation of light in geometrical terms, and that is a very important insight. His insight was a guess, and the reason that Fermat's law is obeyed only it became apparent after we understood the nature of light. So a very deep insight by a brilliant man. And we'll come back to Fermat later in the talk. And of course, that king, master of physics, that icon of the 20th century, Einstein, he also had things to say about light and its relationship to gravity. And right at the end of my talk, I'm going to finish up with Einstein, a good point which to draw conclusions. So, what are we here for? We're here to hear about invisibility. And this is the grand challenge of these new techniques which we're introducing. Can we make something invisible? I've chosen as my icon of invisibility here Peter Pan, partly because his statue is in Kensington Gardens, which is just outside my college, but also because the really important and difficult thing you have to do to make something invisible is to arrange that it doesn't have a shadow. And Peter Pan, if you know the story, was a little boy who lost his shadow. Wendy, of course, sewed it on afterwards, but he lost his shadow. And that's what we need to do, because conventional stealth, such as you have on a stealth bomber, just makes something not reflect light. That's okay if you're in a radar dark environment, so that if the plane doesn't reflect any radar, then you don't see it. But it's not enough if you're in a bright environment. If you play squash, then this is a game you play with a black ball, which doesn't reflect any light. And in fact, it's actually more visible than a white ball, because you play squash in a very bright environment, and the shadow of the ball makes it extremely visible. And in fact, these days, the environment isn't radar dark generally. If you fly over a city, you're flying through a constant chatter of mobile phone conversation, and your passage can actually be tracked by the shadow you leave in those radio signals. So black is not enough, and we've got to get rid of Peter's shadow. That's easy enough to do in Photoshop. But it's a little bit more of a challenge to do it for real. It is interesting to note, though, just how little of the shadow you need to remove before the thing's not really visible. If I was stumbling across Kensington Gardens early in the morning thinking about my lectures, I probably wouldn't notice Peter in the trees there, even though he's 50% there. Unless he moved, of course, and then I'd see him. So how can we make something invisible? Well, there have been various, of course, this is a topic which has challenged people for years, and in fact, there are people who prove theorems in electromagnetism which says, don't even try, it's impossible to make something invisible. So it was quite a challenge. Various people have answered it, tried to answer it. Here's a solution put forward by H.G. Wells, who was a novelist specializing in science topics about the turn of the last century. He was actually a graduate of my college, a graduate in physics. I'd like to boast about that, but in fact he didn't like the place very much, so I shall be rude about his ideas. His idea was, his novel was called The Invisible Man. And the way his man became invisible was he drank a chemical, a magic potion almost, that made his refractive index the same as that of the surrounding air, so approximately 1. And so light would pass through. I don't think that would get past health and safety these days, so we'll write that one off straight away. This is a more subtle approach. And actually, this was an approach which was mentioned at the conference yesterday. So you take an object and you measure its response to light. You measure how it scatters light. And then you surround it by another object whose scattering properties are precisely manufactured so it exactly compensates for this object you're trying to hide. So in this case, we have a high refracting medium, and we surround it with a medium with some negative refraction. You can get such media, I'll talk about them later, and that compensates for the positive scattering here, and the net result is no scattering at all. So that can work. Clever idea, but of course you have to know the exact properties, and if that object changes, then the properties of your cloak must change as well. Nevertheless, it's a feasible scheme, and people are trying to enact that. But this is the much more simple approach which we adopt, and it is simply to make the light avoid the object that you want to hide. And so as light comes along, it does a chicane around the object, but then you don't lose track of where it goes. It doesn't hit the object, so you don't have any scattered light, but you must return the light to the exact same path it was going along in the first place, so that you see what's behind the cloak and not anything to do with the cloak itself. So this is what we want to do. It's a bit like making an analogy between water and light. If you have an obstacle in a stream, a fence post or something in the stream, water flows past it, then a little way downstream from the obstacle, the water will smoothly flow around the obstacle, close up again, and downstream the water is flowing smoothly once more, and you wouldn't know that it had been disturbed further up. Light doesn't flow like that naturally, so we have to find a way of making light flow like water so that it avoids the obstacle you're trying to hide. And that's the approach we shall take. And there's an analogy you can make here with a mirage, and we're going to take our lessons from the physics of the mirage. And I guess many of you will know how this works, but I'll explain it again. So this is Snell's Law, and this is a sort of refraction you see in a camera, an interface between two media, both of constant but different refracting powers. And in each medium, the light goes in a straight line. Now, in the case of a mirage, and here's a road, not a very good picture of a road mirage, where the road's very hot, and if you look at it in the distance on a hot day, I'm sure this occurs many times in Australia, many more times than it does at home, then you see the road appear to be wet. And the reason it appears to be wet is that the hot air in contact with the road is less dense than the cool air above. And this gradient in density translates into a gradient in refracting power. And so instead of being sharply bent like this, the light is continuously and smoothly bent. And if the bending is strong enough, instead of hitting the ground, this ray of light from the sky will wind up in your eye. So you see a reflection of the sky in the ground, and your interpretation of that is it must be water, hence the thirsty traveler in the desert seeing a mirage of an oasis. It isn't at all, it's just the hot air refracting the light. And this is just the continuous bending that we need to achieve to make a cloak, except that this is uncontrolled, it happens randomly. We want to do it in a controlled, precise way so that the light goes exactly where we need it to go. So that's the philosophy of how we're going to proceed. And when we're done, these are the trajectories that the light must follow. Now, to do that, you've got to have two things. One is you have to be able to shape the refractive index in exactly the right way to send the light on these precise paths, because if you don't, then somebody observing the far side, it will be, you know, if you look through some window glass, if the glass is perfectly flat, like a shop window, then you see the products inside the shop window. If it's a little bit ripply, like you might have in your front door or your bathroom window, then you know that the glass is there because the trajectories of the light are distorted. So you must have some very finely contoured refractive index here so that the light is not distorted when it comes out. That's very important, otherwise you can see what's there quite easily. And to do that, we need to exploit a new class of materials that enables us to generate any property we like here. These we call metamaterials because their extraordinary properties go beyond the properties of ordinary materials. Meta, from the Greek, means beyond, and hence metamaterial. And the second thing which we must do, which I'll touch on briefly at the end of my lecture, is if we can get the materials, that's fine. But exactly how do we need to shape them in order that the light goes in this trajectory here? And we have developed a technology called transformation optics, which says that if you want to shove the light along this trajectory, transformation optics will tell you how you must shape the refractive index. So what are these metamaterials we're going to use to make the cloak? They're closely related to ordinary materials. So if you look at glass, why does it refract light the way it does? To understand that, you need to go down to the molecular level, to the silicon and the oxygen, and ask how those atoms and molecules respond to light. And it's the way they polarize that dictates how the light responds. Of course, what you see is not the details of how individual molecules respond. It's some sort of average. There are more than 1 billion molecules of glass in a cubic wavelength, and the light sees an average over that cubic wavelength. But basically, it's the atoms and molecules responding that gives light its properties. Now, the objects which respond don't have to be as small as an atom or a molecule. They could be bigger, and still you could have not billions, but maybe millions or hundreds of thousands of them in 1 cubic wavelength. And this averaging process would take place, and then you would have some average property, but now dictated not by the chemistry, but by the physical structure which you've introduced. So these are little artificial molecules, which in the case of light might be nanostructures, or if you were working at longer wavelengths where you have more room to fit in larger objects, these could even be a few millimeters across. And in fact, it's the radar analogy we're going to use because that's where these technologies have been first developed. So here is one of the first materials which we used. This was built, this all grew out of consultancy I had with the Marconi company on radar absorbing material. And Mike Wiltshire made this little structure here. Its idea was to produce magnetism in a range of frequencies where it was very difficult to find natural materials which were magnetic. What he has here are some little rings made of copper. These are etched on a circuit board. And if you put a magnetic field, an oscillating magnetic field on these rings, then they will induce a current to flow around the rings. A current, in turn, generates a magnetic field. So you get a magnetic response to a magnetic field. And so although you don't have any iron or nickel in this material, you still get a magnetic response because of the structure, again, not because of the chemistry. And this so-called split ring structure has been the vehicle of many experiments over the last 10 years. And by engineering the precise details in this split ring structure, by adjusting the separation between the rings, the diameter of the rings, and so on, you can get pretty much any magnetic response you want out of this structure. So you don't have to hunt around in nature for some magnetic material that does the job. You can simply type it into your computer, send it off to some foundry which will print the circuit board, back it comes, and it has the property you want. It's as easy as that. And this is the technology which was exploited by my longtime friend and collaborator, David Smith, and his team at Duke University. And they built this realization of a cloak. And what you have here is a device which is designed to respond to radar waves. This is going to cloak against radar waves. You can guess why people might be interested in funding that. In the center here is a hidden cylinder which the radar waves are not going to be allowed to reach. And to control the flow of the radar waves, we're going to introduce a metamaterial here. And the function of this metamaterial is to take the light, the radar waves, and guide them around the obstacle and shoot them out the other side. This is a graph of the gradient in the refractive index as you go from the innermost to the outermost ring. And to tune the response of this setup, the physical structure of these little split rings, this is a development from the split ring here. So you have a copper circuit going round, a capacitive element in here. And by adjusting the precise details of the geometric structure, you can engineer this gradient in the refractive index from the inner to the outer part of the cloak. So when you've done that, oh, yes, sorry, here is some more detail of these are the parameters which they tune to get exactly the response they need. And now when you're done, you put that in a chamber in which there's a source of microwaves of radar frequencies. This is a two-dimensional chamber with the microwaves confined between two heavy aluminium plates. This is some radar-absorbing material so that the radar waves don't bounce around too much. And this is the cloak. And the idea is that these radar waves should be grabbed by the cloak, guided around and out in the schematic way I showed you in the diagram a few slides back. Now, this was a remarkable achievement by the Duke team, I might say, because the design for this cloak, the specifications of the refractive index and so on, had been produced only 6 months earlier in a paper which I wrote in Science. And I thought that would be that for a year or two whilst the experimentalists put something together. But these guys built the cloak within 6 months. And that gives you an idea of the power of this metamaterials technology, how quickly you can move to realize theoretical ideas. So what have we here? This is the strength of the electric field in the cloak. And this first panel here shows a computer simulation of what the waves would do if you got the ideal realization of the parameters which we specified in that earlier paper. And so these are the rays. Think of them as rays of light. They're actually rays of radar waves. And these are the wave fronts for those people who know what wave fronts are. And as I suggested, this device just takes these rays of light, steers them right around, and has them emerge so that they go in the same straight line they would have done had there been no cloak or obstacle there. So this just says that the theory does what it says on the tin. Now, in order to realize the cloak, the Duke team had to make some approximations. Because they wanted to do it real fast. They knew that the competition would be on their tail pretty quick, so they wanted a demonstrator as quick as they could. So they made some approximations. And one of the main approximations they made was that the materials they used had some absorption in them. So some of these rays don't quite make it to the other side. You lose a few of them along the way. And you can see that in this, again, a computer simulation, but using the experimental parameters they knew they could realize. And these rays, they're making a good job of going round, but they're a bit wobbly on the other side, aren't they? So it's not perfect. And you can see that these wave fronts are not as intense as they should be here. So what you'd see if this were visible light, it isn't, it's radar waves. What you'd see if this visible light is not something which is completely invisible. You'd actually see a little grey patch in the sky because not everything will get through.